So we said that Huckel's rule states whether it's not something that's aromatic if it's cyclic, fully conjugated, planar, and has 4n plus 2 pi electrons. And these four factors are easy to remember, but what's really the reason behind the aromaticity phenomenon? And for that we need to look at the molecular orbital description. So let's look at benzene first. And the best way to visualize this is to use a process known as Frost circle. And Frost circle is really inscribing a polygon inside a circle. So the first thing we do is draw a circle, and then we need to inscribe a polygon so that the point of the polygon touches the bottom of the circle. And so in this particular instance, a hexagon will be drawn for the benzene ring. So that's the polygon that we're talking about. And so if we're going to draw a benzene ring inside, we're going to use a hexagon, and this hexagon will look like this. So we fill in the rest of the polygon, and each point that touches the circle corresponds to a molecular orbital. So the midpoint of the circle is the non-bonding energy level. So we always define the non-bonding energy level as the middle, and so this is consistent with what we've had previously. And that any other point in which the polygon touches the circle is a new molecular orbital. So we obviously have one down at the bottom, right? We have two here below the non-bonding level. We have two above the non-bonding level, and then one at the top. Okay, so what we then do is we kind of break those molecular orbitals out of the polygon. So we have a set of molecular orbitals that essentially will look like this. We've got one here, we've got two there, we've got two here, and we got one at the top. And so we can label these as follows. We can label these as a pi 1. We can label this one as pi 2 and pi 3. And notice that pi 2 and pi 3 are degenerate. They have the same energy. Likewise, pi 4 star and pi 5 star are degenerate. And then we have pi 6 star at the top. And how many electrons do we have overall total in benzene? We have 6. And so we've got electrons in pi 1, pi 2, and pi 3. Right? So we don't have any electrons at the non-bonding energy level, and we don't have any electrons in the anti-bonding orbitals. And so the aromatic stabilization energy, as we described earlier for benzene, is 35.5. And so this particular diagram sort of demonstrates that you have this aromatic stabilization energy. So what do these orbitals actually look like? Well, let's actually try to copy this over and see what the orbitals actually look like if we use our rules of linear combination of atomic orbitals and draw some nodes. Okay, so let's draw out the orbitals again. So we've got pi 1, pi 2 and pi 3, pi 4 star, and pi 5 star, and then pi 6 star. So let me just label those. And again, we've got 2 electrons in pi 1, pi 2, and pi 3. Okay, so let's draw this out a little bit larger. So I've got pi 1 here, and pi 1 has 0 nodes. It's got 2 electrons in it. So 0 nodes in it. And so if we were to draw it, it would look like something that doesn't have any nodes in it. So let's look at a benzene ring from the bird's eye point of view. So if we're looking at a benzene ring down from the side, what we'll notice is we've got atomic p orbitals that kind of look like one phase is shaded, and of course behind here is another phase that's unshaded. All right? And so we've kind of turned this benzene ring on its axis. So this used to look like kind of like this. All right, so this benzene ring here is out of the plane of the screen, and so if we're looking at this from the bird's eye point of view, you can see that only one side is shaded, right? So this is the bird's eye view. Okay, so that's what we're drawing here, is the bird's eye view. So let's be consistent as we go through this. Let's continue to draw the bird's eye view. And so then we've got, over here we've got pi 2, and here we've got pi 3. And so let's label those. And we know in the next energy level we have one node. All right, and so we've got 2 electrons in each of these. We need to draw what this might look like. All right. In one particular instance, we might have a node that goes, let's say, directly through those 2 carbon atoms. And as we cross the nodal plane, what we're going to do is we're going to change the phasing. So now it's an unshaded piece of the atomic p orbital. On the other side, we've got a benzene ring, and maybe it will be it will have its node directly through the bond instead of directly through the atoms. And so in this particular instance, it's going to have a little bit of a difference in the size. The middle atom is going to be bigger, okay, than the edges. Okay, so that's pi 2 and pi 3. Let's move up. Let's do pi 4 star and pi 5 star. Okay, those don't have any electrons in them. Here now we have 2 nodes. No electrons in them, and so let's draw out something that would have 2 nodes. Let's say we've got a system that has a line through the vertical and a line through the horizontal. We would have a system that would look like this. Let's say this one is shaded, that one's unshaded, this one is shaded, and that one's unshaded. Okay, in the case of pi 5 star, we can have a benzene ring in which we've got sort of an X shape. And so this time we've got 2 nodes that are going through the bonds. And so let's say we start here with shaded. This one would be big and unshaded. This one is shaded. This one's shaded, big and unshaded, and then of course shaded again. And then finally we have pi 6 star, no electrons. It's going to have 3 nodes. And its shape is going to look like a combination of pi 4 star and pi 5 star. So we've got this sort of X shape again, but now we've got a node directly through the horizontal. And so we're going to have a system that looks like this. So as we go across each particular one, we're going to change the phasing. And so we've got big lobes and small lobes. Okay, so this method can be used to determine how many nodes, what the structures look like, and placing the electrons inside. All right, so with this method, we can probably see that you've got, if we got our non-bonding level right here, we've got only electrons in the bonding part. And so can this method predict when something is anti-aromatic, or explain why it's anti-aromatic in the first place? So let's actually try to do cyclobutadiene. So we know that the structure of cyclobutadiene looks like this. It's 4n pi electrons, right? And so this is anti-aromatic. All right, so let's do frost circle. What we're going to do is we're going to inscribe a polygon inside a circle. So the polygon that we're going to inscribe inside this circle here is going to be a square. And so the rule is that you place one side of the one point of the polygon at the bottom, and then you place the other points on the edges. And so when we do that, we're going to have a point touch the bottom, a point touch directly on the sides, and then at the top. And so each side, each point that touches the side of the circle is going to be a molecular orbital. All right, so if we have these molecular orbitals, let's draw them outside of the circle like this. We're going to have 4 molecular orbitals. This one's going to be pi 1. We say that this is pi 2, but again, it's at that non-bonding energy level, so it's going to be a non-bonding orbital. This one is pi 3, but it's also at the non-bonding energy level, so it's an n. And then we have, of course, pi 4 star. And if we put in our electrons, we've got 4 electrons total, so we're going to put in 2 electrons to the pi 1. And then we need to place 2 electrons in both pi 2 and pi 3. Right? So 1 electron each goes into pi 2 and pi 3. And now what we can see is that the 2 orbitals, pi 2 and pi 3, are degenerate, and they lie at the non-bonding energy level. So each orbital gets 1 electron, and this suggests that really cyclobutadiene doesn't exist as a pi bond. Right? It really should be drawn as a diradical. And so the reason why it doesn't like to pair up those electrons is because then it would be anti-aromatic. It would have 4n pi electrons in a cyclic system that's completely planar. And so what happens is it sort of becomes like a diradical in which those electrons aren't paired up. And so since paired electrons are lower in energy, this would make the system really reactive, right? And so in this case, what happens is it kind of it blows up, or it does what's known as a retro 2+2. So instead of having this diradical, which is really reactive, what we can get is a retro 2+2, and what will happen is you'll get the 2 electrons moving like this to give you 2 molecules of acetylene. And of course, acetylene is highly flammable. The other thing that could happen is you could take 2 of the radicals and pair it up with another pair of radicals like this, and get a 2+2 and sort of dimerizes in this case. And so you can get a dimer to form. And this would lead to a structure in which you've got 3 cyclobutadienes connected together. And this is a system that is similar to some natural products called the laterines. All right, so we can kind of understand here why cyclobutadiene is so unstable. Might we be able to draw out what the orbitals would look like for this? Well, we know that in pi 1 there's 0 nodes, and so we're going to have a square in which we've got all bonding throughout those 4 atoms. Okay. In the case of pi 2, all right, we've got 1 node. Let's say that node is going directly through the center of those 2 atoms. And so as we cross the nodal plane, we're going to change the sign. So it changes from shaded to unshaded. In the case of pi 3, we've got, let's say now we've got a node that goes directly through the bonds instead. And so we've got, let's say, 2 lobes that are shaded here and 2 lobes that are unshaded there. Right? And this is because there's only 1 node in pi 2 and pi 3. In the case of pi 4 star, we've got 2 nodes. And so the shading here is going to be, we've got 2 nodes kind of looking like an X. And as we cross the nodal plane, we're going to change the phasing. And so it's going to look very simple, alternating up, down, up, down. Right, so What's happening here is that anti-aromatic compounds, in the case of like 1,4-butadiene here, anti-aromatic compounds will do everything in their power to break that conjugation, right? Including becoming a diradical or puckering the ring so it's not planar anymore, or dimerizing to give you some extended structures. And so what happens here is that you've got two electrons in a non-bonding energy level. Sometimes you'll have electrons that are in the anti-bonding orbitals. And so this will explain why these kinds of systems are anti-aromatic or aromatic. And so what you should do is try a couple of these molecules out for size. Try a couple of them out yourself. And so let's draw this in terms of frost circle. You know that a lot of these will be able to you'll be able to assign the aromaticity or anti-aromaticity of these molecules just by using Huckel's rule. But can you explain that they're aromatic or anti-aromatic simply by doing frost circle? Okay, and so let's do these molecules on your own and see if you can come up with the correct answer.